So, welcome back to our video lectures on projective geometry. We are still dealing with conics, and the lecture today will be very geometric. In our last lectures, we learned how conics can be associated with a projective scale on the curve that defines the conic. And you know that harmonic sets as well as quadrilateral sets are important concepts for points on a projective line. And we will now see how these things look at the level of a conic. Once more, a disclaimer here: throughout that lecture, all the conics that we will consider will be real and non-degenerate. So they will be either ellipses, hyperbolas, or parabolas. So we will start with quadrilateral sets on conic. Although they at first sight seem to be more complicated than harmonic sets, it turns out that they have a very, very nice representation on the level of conics. And for that, consider this extremely simple drawing that I've done here. So I simply take three lines that intersect at one point, and I cut these three lines with a conic, and I get 6 points on the conic. So it's perhaps one of the most simplest things you can do with some lines and a conic. Draw a special situation with the three lines. It means they should meet in a point, and just intersect that with a conic. And the amazing fact that we will prove next is that these 6 points here, if you consider the conic as a projective line, they will play the role of a quadrilateral set. So if you apply the methods of our previous lecture, where we defined how to consider this conic here as a projective line, then these points here paired in the natural way, so A comes with A prime, B comes with B prime, and C comes with C prime, form a quadrilateral set, and I give it such an index C to indicate that we are really doing that on the conic. So how are we going to prove that? We are proving it by, without loss of generality, moving to a very special case where we can do the calculations in the easiest way possible. And the special case to which we will go is the following here. We will, by a projective transformation, move our conic to a parabola. This parabola will in a sense be the calculation frame of what comes next. So our points are mapped to points on the parabola, and one of those points we will map it to infinity and use it as the points from which we draw lines to all the other points to calculate cross ratios and quadrilateral set relations. So let us look at this picture here, and as a first part at this line here for measuring our cross ratios. And now we do a stereographic projection from point C prime to the line. So C prime is at infinity, but it's still on the conic because the parabola meets the line at infinity in exactly one point, and projecting down from that point really means to make an orthogonal projection down to our line. And before we continue, I want to consider a little sub-configuration of what we have seen here. Just take 2 points, their projections down here, and this point of intersection, and I will give you a nice algebraic relation between these values here. And for that, assume that our line here is equipped with a scale that corresponds to the real numbers, and if you do so, our points x and y have some coordinates x and y. And as a next thing, assume that the parabola here was just the standard parabola, and by that we can write down the coordinates of those points here. So in the R2 it would just be x and x squared and y squared. And now I tell you what is the coordinate of that point. So the x coordinate of that point is clear, it should be at 0, but the y coordinate, what is the altitude of that point? And it turns out that the altitude of that point is exactly minus x times y. And this fact is just one of those little miracles that make things work. So how to prove that? Well, we just have to prove that these 3 points here are collinear, and we can simply do that by checking whether a certain determinant becomes 0. So the determinant are those 3 points here in standard embedding. So you have x squared 1, y squared 1, and our white point 0 minus x 1. And well, if you calculate the determinant, it's just obvious that it has to be 0. So you get x times y squared, this is this term here. You get y times minus xy, which is this term here. Then you get 0 times something, which doesn't count. Then you get x times xy, but you get it in the summand where you have to subtract. So you get x squared y, and you get y times x squared, which has to be subtracted as well. And you immediately see that the white and the green terms cancel and you get a 0. So these 3 points here are indeed collinear. I must show you one application of that in mathematics communication. We have a model of that in our mathematics exhibition X Quadrat in the Garching campus of our university. So we really have built a parabola, and we have a little rope that we can attach between points, and by that multiply numbers by getting their intersection with the y-axis. And we really explain this device even to little kids who learned already about multiplication. So this is really a nice and funny gadget, and we can now apply that to prove our quadrilateral set relation. So let me come back to the picture that we had before. Now we have not only one of those lines, we have 2 of those lines. So we have an x1, y1 and an x2, y2, and what I want to prove is that if those here intersect at this point, and this means that the product of x1, y1 must be the same as the product of x2, y2, then we indeed have a quadrilateral set equation. And from now on it's just doing the calculation. What does it mean for being a quadrilateral set equation? It means that this product of 3 determinants equals this product of 3 determinants, and if I write down what you get in each of the factors, you get what I've written down here. So for instance, if you take this determinant, always think of it in the standard embedding, you get x1 minus y2. Here you get something that involves point infinity with coordinates 1, 0, and you get exactly that expression. If you factor it out, you see you get that expression. And if you look here, you see the term y2, y1 occurring on both sides, so you can subtract this as well, and you are left with x1, y1 equals x2, y2, and this is exactly the case because these 3 lines, the 3 green lines, meet at this point. So we really proved our quadrilateral set relation for the general case, because without loss of generality we could move to that projectively transformed setup. Here comes a different drawing of this theorem, and one that I really like for aesthetic reasons. So take your quadset relation that you have here, and how can you check that it is a quartet relation without calculating just graphically. So what you just have to do, you take an arbitrary point on your conic, you view your 6 points from that point, and if it's true what I told you, then these 6 points here have to be in a quartet relation, which you can simply check by this configuration of 4 lines. And if you take arbitrary points here for the first 3 choices, then the intersection of the last one will already be determined by the rest, and it will be exactly on the last line. So this picture here, which almost made it to the cover picture of the projective geometry book, is a graphical explanation or a graphical picture of this nice quadrilateral set relation. So as a next thing, I want to give you some applications of this quadset relation, and for this we'll move our points to that position that we have here. So you know there is a quadset relation between those points, and now draw a few more of those configurations in your picture like that. And you may recognize that I've drawn an instance of Pascal's theorem here. So what you have here, you have 6 points on the conic. You connect them in such a kind of zigzag path that we have here. And then those 3 intersections that you have here will be automatically collinear. This is a kind of generalization of Pappus theorem. And how to prove it, and we can prove it in a very straightforward way if we use the quadrilateral set relations. So what we have to prove is that if this relation here is present, the one between the B's and the C's, and if we know that this relation here is present, then automatically the last relation, this one here, will also be present. So in terms of quadset relations, we only have to prove that if we know that this is a quadset and this is a quadset, we can conclude that this here is a quadset. And this can be done by simply writing down the equations of the quadset relation. So this here is the first relation, so this is the one between the B's and the C's. This here is the second relation, and from that we want to conclude the third relation. And for that we simply can do the following thing. We multiply both left-hand sides and both right-hand sides and cancel out everything that occurs on both sides. So if you look here, you see, for instance, the term cy occurs here and can be cancelled out. And the term, let's see what occurs on both sides as well. The term c prime occurs here, and last not least, the term xc prime occurs here. So if you multiply the left sides and the right sides, cancel out the underlined terms, you will recognize that this is this factor, that this here is this factor, and that this is this factor. So on the left side you have exactly what you've written down here, and on the right side similarly you get the first factor here, you get the second factor here, and the third one, you get it here. So you see, if you have those two equations, multiply them together, cancel out. Being able to cancel out is a non-degeneracy condition, and then you derive the last quartet relation, which proves Pascal's theorem. So we ended up with a very, very elegant proof of Pascal's theorem. And if you look at it, these points x and y, they only played a role in the proof, but not in the theorem. So they play the role of some kind of auxiliary points. So next application is, you remember when we talked about von Staudt construction, I told you that, for instance, if you have a projective scale, 0, infinity, x, y, and 1 x times y form a quadrilateral set. And you can turn that into a nice multiplication device. So assume you are given a conic with a projective scale, and you know where your points 0, 1, and infinity are, then you can calculate the product of 2 points x and y, so this here is x, this here is y, by an extremely simple construction. Just connect those points, intersect it with the line connecting 0 and infinity, you get a point of intersection here. And if you connect 1 to that point here, then you get a line that intersects your conic at the scale point that corresponds to x times y. So here you see the really deep equation that -2 times 3 is -6. Let me give you a few more examples. So here you see 2 times -2 is 4, and in the next example you see that -2 times 4 is -8, or -3 times 4 is -12, and it may happen that things become really narrow, and then you can still move your projective scale and work with that. So you can, if you have a dynamic version of that, really calculate even with pretty high numbers. So here you see that -6 times 3 is -18. Well, you can even move around your point at infinity and get quite distorted images of what you have here. So this was one application. Here comes a very important application, which corresponds to a limit situation where two pairs of points coincide. So assume we consider the quadrilateral set of 4 points where we take the first pair to be twice the same point and the second pair to be twice the same point as well. In one of the earlier lectures we proved that if this is a quad set, so AA, BB, CD is a quad set, if and only if A, B, C, D is in a harmonic position. And this gives us a very nice and simple construction for a point that is in harmonic position to 3 other points by simply applying this quadrilateral set relation. So we draw the connection of A and A. We are in a limit case, so we just have to draw the tangent here. We draw the connection of B and B, again a tangent, and now we construct the point D that is in quadset relation with respect to those letters I've here, and I can simply do that by taking this point of intersection and connecting it with C, and our point D is exactly at the position down here. So these 4 points that I've drawn here are now in harmonic situation on our conic. And you know, harmonic situation is a very symmetric thing. If I interchange the role of C and D and A and B, I must get the same relation. And just as a remark here, if I do the same construction in the other direction, that I first construct the tangent to C and then the tangent to D, get that point of intersection, connect it with B, then it will automatically also go through point A. So you see that's completely symmetric. So this in turn now gives us the possibility to finally construct a projective map that leaves our conic invariant and moves 3 points to 3 other points. And we will do that as a kind of final example here. So assume that you want to have a projective transformation that maps A, B, C to A prime, B prime, and C prime, like that here. And you wonder how to define that projective transformation. Well, a projective transformation is defined by 4 pre-image pairs of points. We have 3 of them. We need a last one, and the last one can simply be obtained by taking 2 points that are in harmonic positions with respect to the other 3. So we already constructed point D, and now we will construct a harmonic point with respect to those 3 points just by the same construction, and we will end up at that point. And so we finally also have to map D to D prime. And I told you in our last lecture that you get a projective transformation that leaves C invariant if the cross ratio of 4 points is preserved. And here we have exactly this situation. Both quadruples of points have a cross ratio of -1 because we constructed it like that. And in this way you can define the projective transformation by the image of 4 points. So we have a constructive way now of, when I give you 3 points of a conic and 3 images of those 3 points on the conic, to construct a projective transformation that leaves the conic invariant. Let me end here with a few pictures. So here you see a smiley, and the smiley has a boundary which is actually a circle. A circle is a conic, and here I have 4 points on that circle, and actually those 3 points I put at 3 positions here, and the last one is constructed by this harmonic construction. And here I show you what happens if I consider projective transformations that leave the boundary of our smiley invariant but move all the rest. And what you observe here is that really if I do this construction, the circle here remains fixed, but both the exterior and also the interior of that picture get quite distorted. But by our procedure we really can keep the shape here invariant to be a circle. Here is another example of that, which is a little bit more geometric. I've drawn it with my ornament drawing app iOrnament. So here you see a kind of mandala-like pattern, and you see the leaves of that mandala are located at this circle here. And if I do the same as I told you before, then you see how this ornamental pattern gets perspectively distorted, but not in an arbitrary way. It gets distorted such that this central flower here really remains within the circle. And you see here, for instance, how the center gets mapped to different points of the circle. Believe it or not, this will be relevant later on when we are going to study hyperbolic geometry, and we will see that these transformations that leave a conic as such invariant are exactly the transformations in a hyperbolic geometry. This will take us busy to get there over the next, I would say, 6 to 9 video lectures, and now we embark to a new journey about different kinds of geometry, starting with our next lecture. See you there!